welcome to this lecture. For me, it's quite early morning, and I guess for some it's still evening, and for some it's probably afternoon. So thanks for being here, and thank you to the organizers for inviting me to give this lecture. So my name is Nele Mentens. I'm a professor at KU Leuven in the electrical engineering department and in the cryptography research group. And also at Leiden University in the Netherlands, where I am in the computer science department. So this lecture will be about FPGA design for cryptography and security. Yes. So first, to give you a bit of context, when we say security and when we say FPGAs, then that can actually mean two things. So on the one hand, there's the security of FPGAs. And on the other hand, there are FPGAs used for security purposes. So when we say security of FPGAs, then we typically mean the protection against reverse engineering. So against reverse engineering of the bit stream, for example, protection of against cloning of a certain FPGA design, protection against the theft of intellectual property that is contained in a certain FPGA design, etc. On the other hand, there's the use of FPGAs for security. And what I will be talking about in this lecture is on the right-hand side of this slide. So the use of FPGAs for, first for cryptography, and also for network intrusion detection. So that is what this lecture will be about. So first of all, I'll give some basic introduction to what FPGAs are actually, and then I'll say something about cryptography on FPGA and about network intrusion detection on FPGA. And apologies for my voice, I actually have a cold, so it's good that this is a hybrid meeting and that I'm not traveling there. So, but I hope it will be fine until the end. So first of all, what is an FPGA? An FPGA is a field-programmable gate array. And it's actually a regular or the basic architecture of an FPGA. And I'll say something later about extra things that popped up in later generations of FPGAs. But the basic structure looks like this on the slide. So it's a regular structure of configurable building blocks, let's say. And I'm using here the terminology that is being used by Xilinx or AMD, one of the largest FPGA vendors, but I could have used the terminology of other FPGA vendors, but the basic principle is the same. Let's say the most important building block here is the CLB, or configurable logic block, and I'll show you later what I think somebody probably has to unmute. Yeah, thanks. I'm sorry. So this configurable logic block is actually where we program the functionality that we want on the FPGA. Then we have a switch matrix, which is used to connect the different configurable logic blocks to each other. And then there's input-output blocks that make sure that the FPGA can communicate to the outside world. If you compare this to the architecture of a CPU, for example, then in the CPU, you have like the computing heart or the ALU that executes all the operations, let's say, and many things around that to make sure that the ALU can do its job, and you write software code that will then be run on the CPU. In this case, what we do is we write hardware description code, let's say, hardware description language code that will be mounted on these CLBs, such that they can actually execute what needs to be executed, but all in parallel. So all the CLBs can be programmed and work in parallel. While in a CPU, you sequentially execute instructions on the CPU. So if we look inside to this CLB here, then we see that it typically, so there are some other building blocks, but the main building blocks are a lookup table. And actually in modern FPGAs, these lookup tables have more than 4 inputs and also more than 1 output. So this is pure logic. So this is a lookup table in which we can implement any logical function. Then there's a flip-flop, a storage element for 1 bit that can either be bypassed or can be used after this lookup table. Then the switch matrix, that was this building block here, which is used to connect the CLBs together. A basic basic architecture of such a switch matrix could be this one. So, for example, we have 2 lines crossing. Then we use a number of transistors or switches to determine which line should be connected to which one. For example, the top line can be connected to the bottom line when we make sure that this transistor, that this transistor is conducting. Yeah. So what I said was the basic structure of an FPGA is like this. So we have like a regular structure of configurable logic blocks that can have a storage element and also some logic functionality. But like I said, this is only the basic structure, and actually in modern FPGAs, there's a lot more things or functionality that are present. So when we look at the evolution, for example, of Xilinx FPGAs, then we can see that in one of the first FPGAs, there was only this configurable logic. And with configurable logic, I mean what was there on the slide, like the switch matrices, the CLBs, and the input-output ports. I also put the technology node here. So this was in 0.25 micrometer technology. But then FPGA vendors started to realize that some functionality, it would be more efficient to implement some functionality in more dedicated blocks. For example, the first thing that happened was that embedded memory blocks were added. And in Xilinx terminology, these are called block RAM. So in one of the next generations, block RAM was added next to this configurable logic. Because in previous generations, when there was no block RAM, when we then needed like embedded memory, that would only have to be implemented on the flip-flops in the CLBs. And this is not an efficient way of storing data. So this was one advancement or evolution. Then in one of the next generations, other building blocks were also added. And this was mainly done as a consequence of requests of customers. So Xilinx and also FPGA vendors in general, of course, are aware of the applications for which their FPGAs are used. And in order to make those applications more efficient, a number of dedicated, so hardwired ASIC-like building blocks were added to the FPGA. And one thing that was added, for example, were multipliers. Because if you have to do, for example, a 16 by 16 multiplication, then it's not that efficient to do that using just using the CLBs. So dedicated multiplier blocks, I think they were 16 by 16 at that time, were added to the FPGA. Also, in that generation of FPGAs, a dedicated or embedded processor was added, or actually multiple of them, such that they could also be used together with the configurable logic. And then also Rocket IO was one example of something that was added to have like faster input output and a digital clock manager that allowed to use or to work with multiple clock domains. Then some more things advanced, and also the blocks that are here in dark blue, there were updates on these building blocks also. It doesn't mean that they because I make them dark blue, that they stayed exactly the same as in the previous generation, but I'm just highlighting new features. So one example of something new in one of the next generations were Dsp Slices, or digital signal processing blocks, and where we could do like multiplications with the multipliers. In this case, with Dsp Slices, we are able to do like a times b plus c, so multiply, accumulate operation, which is very useful in many applications. Then next generation, one thing that changed was that the Dsp slices were updated. For example, like a pre-addition was added. So instead of a times b plus c, it was now possible to do like a plus d times b plus c. And this was useful for also multiple applications. The digital clock manager was also improved. Instead of using DLL, now phase lock loop PLL was used. And then mainly the Dsp slices were updated and improved. Also, these embedded processors, the PowerPC, were removed, but the support for having like embedded processors in the configurable logic was then improved. And one more addition in one of the next generation of FPGAs was the addition of analog to digital converters. So now it's also possible to use some pins as analog pins in the FPGA, and then the conversion is done on chip. So this is, you can also imagine that this is useful for many applications. Then one more thing that changed in the upcoming or in the next generations of Xilinx FPGAs was like high-speed Ethernet interfaces. For example, 100 gigabit per second Ethernet interface, and then also high bandwidth memory, which is very useful for high performance computing applications. And then one of the latest advancements are the versatile FPGAs of Xilinx, which are actually have like a very high performance AI engines together with configurable. So this is, these are just examples of things that changed in these FPGAs, and these are also not all new generations of FPGAs. So I just tried to sketch a bit what the changes were over the years. But as you can see, an FPGA is no longer just a matrix of configurable logic, but FPGA vendors made a big effort of making FPGAs much more efficient for specific application domains. And this also led to the evolution that FPGAs are definitely no longer only used as prototyping devices for ASIC designs, but are also used really in end products, especially because they became so efficient thanks to these dedicated building blocks. And also the good thing is that since FPGAs are always produced in high volumes, FPGA vendors can follow the latest technology nodes. So when you buy an FPGA, you always have access to those latest technology nodes. And of course, higher efficiency also goes with going to a newer technology node. So sometimes it's better to go for an FPGA that is made in the latest technology node and has these efficient building blocks than to go for an ASIC that would cost you very, very much if you would want to go to this newer technology. I'm very sorry. So this is about the architecture of FPGAs. Now, how do we configure FPGAs? We know that when we try to program CPU, we write our code, for example, in C or any language we use a compiler. And then the program is actually stored in the program memory and executed sequentially on the CPU. When we want to configure an FPGA, what we generate is configuration data in the form of a bit stream. And then these bits are loaded into the configuration memory of the FPGA. And this configuration memory can be made in many technologies. And so there's the one-time programmable configuration memories based on fuses or anti-fuses. And there's non-volatile configuration memory based on flash technology, and volatile configuration memory based on SRAM technology. And actually the multitude of FPGAs on the market are SRAM based. So what is the advantage of SRAM based configuration memory over flash configuration memory? Well, the density is higher, so you can store more bits at the same area. The downside is that it has a higher power consumption, and that we also need like onboard or on-chip non-volatile memory to store the bit stream when we power down the device. But that configuration speed is also higher. Okay, then what do we use these configuration bits for? So we have this bit stream of zeros and ones that are loaded into the configuration memory. How do we use them? We use them in the configurable logic block, which I showed earlier, to determine whether this flip-flop needs to be bypassed or not with this multiplexer, but also, of course, to configure the lookup table. And if we have when we have a 4-input lookup table, 4-input 1-output lookup table, then we need 16 configuration memory bits to program or to configure this lookup table. Why do we need 16 bits for a 4-to-1 lookup table? Well, if you with 16 configuration bits, we can have 2 to the power 16 possible output functions. So when these 16 configuration bits are all 0, then that actually means that for any, so these are the inputs of the lookup table, A, B, C, and D, because we had a 4-input lookup table. And this is the output of the 4-to-1 lookup table. But we have here 2 to the 16 possible outputs that are determined by the 16 configuration bits that configure the lookup table. So when these 16 configuration bits are all 0, then that means that for any combination of the 4 input bits, the output will be 0. When or if these 16 configuration bits are 1, 0, 0, 0, all zeros, then that means that only for one combination of the 4 input bits, the output will be 1, and for all other combinations, the output will be 0, and so on and so on. So in this way, we can make any functionality. Also, for example, Z0 is the same as the function that just outputs 0 all the time. Z65535 is the same as function that always outputs 1. Here, somewhere in between, where we have half ones, half zeros, this output actually always corresponds to the input A. So this function is just A. And then in the same way, we can make any kind of logic function with 4 inputs and 1 output. We also use the configuration memory bits in the switch matrices to determine, oh, I lost one line here, apparently, to determine which lines should be connected to each other. So how do we design a digital system on an FPGA? Well, first we need a design description. So we can do this with schematic entry. So most of the FPGA design tools foresee the option where you can just place blocks and visually see like what you are building, but this is only advisable for very small designs. Then there's also hardware description languages like VGL or Verilog, in which we describe our design for the FPGA. And there's, there's higher level languages, typically also sometimes also for specific application domains. And these higher level languages allow us to describe our design in a higher level, more software-like language that can then also be synthesized in the end to bitstream. So this is the description. And when we want to implement the system, we need to create a bitstream that contains all our configuration data. And this can be obtained after synthesis and placement. This bitstream will then be uploaded either via a download cable, can be parallel cable, USB cable, etc., connected to the PC or from onboard ROM. Okay, give me 1 second. I'll just yes, I'm back. So we had a look now at what FPGAs look like and what the architecture looks like, what the design flow looks like. So now this lecture is about the use of FPGAs, first of all for cryptography and next for network intrusion detection. So first we have a look at cryptography. So here is a timeline with some examples of cryptographic algorithms that have been standardized over the years. So these are some examples, and there are definitely more. Functionalities of these algorithms are symmetric key encryption, hashing, key exchange, digital signatures, public key encryption. And if we look at the algorithms on the timeline, then we can see that there have been a few that do symmetric key encryption. For example, there was the data encryption standard in 1977, or DES, which was then found to be no longer secure after a few years or after a few decades. And then AES was announced as a new standard in 2001, so the advanced encryption standard. Now for these algorithms, for all these algorithms actually, it's important to see what the key lengths are that are necessary to have proper protection against all sorts of attacks. And for these symmetric key encryption algorithms, when you look at keylength.com, then you can see advice on which key lengths to use. For symmetric key encryption, and these key lengths are important because later when we talk about how to map these algorithms on FPGA, then it's important to see that for some algorithms, the key lengths are much larger than for other algorithms, which is important because we want to use the FPGA for its parallel computing capabilities. So for symmetric key encryption, it is advised that when you use like existing implementations or systems, that an 80-bit symmetric key is still okay, but should not be used in new systems. So if you want to go for new-term protection for security for at least 10 years, then 128-bit key is advised, and for long-term protection, a 256-bit key is advised. And that was also where it went wrong with DES, because there the effective key length was only 56 bits, which is much lower here. So that can easily be, DES can easily be broken with, quite simple attacks actually. And of course, it all depends on the computing capabilities of modern computers, clusters, etc., what they are able to do with in terms of attack capabilities. Then the RSA algorithm, which was also published in 1977, can be used for digital signatures and for public key encryption. In digital signatures, so this is a public key cryptography algorithm, which means that instead, like as opposed to DES and AES, where we had symmetric key encryption, their sender and receiver, or the two entities that communicate with each other, have the same symmetric key that can be used on one side for encryption and on the other side for decryption. Now, in this case, with public key cryptography algorithms, the key pair consists of a private key and a public key. And in a digital signature, the sender uses his or her private key to place the digital signature, and a receiver that has the public key, and this public key is public, can then verify whether the signature is correct. In public key encryption, it goes the other way around. There, the sender uses the public key of the receiver to encrypt the message. So anybody can encrypt the message, actually, anybody that has the public key. And then the receiver uses the corresponding private key to decrypt the message. And it's only the receiver that can have this private key. Now, RSA is based, or the security of RSA is based on the fact that it's difficult to factor large numbers that are composed as multiplication of two primes. And then the advice here is that this factoring modulus is for legacy systems 1024 bits, but for near-term protection should be 3072 bits, and for long-term protection 15,360 bits, so very large actually. The Diffie-Hellman protocol, which was published in 1976, can be used for key exchange. In this case, the underlying group that is used in which all the computations take place should be of a certain size that is listed here, and that is similar to this factoring modulus. And the key that is used should also be of certain size, which is listed. Then we have the digital signature algorithm, which is also based on, sorry, that I should have said, on discrete logarithms. So the crypto systems that are based on discrete logarithms, or the security of those systems is based on the fact that it's very difficult to compute a discrete logarithm, which means that if you have like a modular exponentiation, that it's very difficult, like when you have the result of the exponentiation available, and also the base number, that it's very difficult to get the exponent. Then there's also elliptical cryptography, which makes use of much smaller key lengths, and the key lengths are listed here. So they are similar as same as these discrete logarithm keys actually. And then there were multiple standards over the years for hash functions. So a hash function is a function that maps an input of arbitrary length to an output of fixed length. And for hash functions, what is here in this list is actually the size of the output of the hash function, which should also be chosen. When we look at these traditional cryptographic algorithms, actually, then what are the challenges for implementing these? First of all, as you can see here, for many of these, we need to do operations on very large numbers. So that's a challenge. Plus also, for many of these algorithms, we need to do finite field arithmetic, so modular operations, which are more complicated than just operations on integers. So we need to do operations on large numbers and also more complicated operations than those that are just done on integers. So what is the implementation approach? When we look at FPGA design, of course, we can exploit, or why are FPGAs useful here? We can exploit the parallelism that we can have on FPGAs. So we can really implement these operations completely in parallel on an FPGA. We do not need to do sequential operations. And then, as I said before, there are these dedicated building blocks that are there for specific application domains. Well, it's these DSP blocks that can, for example. Sorry? Hello. Is there a question or? Hello? Okay. So these DSP blocks on the FPGA that can, for example, do multiply, accumulate, can also be used for finite field arithmetic. And the embedded memory blocks are, of course, also very useful, the block RAM, to store intermediate results of computations. And then some example architectures of older, of these traditional cryptographic algorithms where modular multiplication was important. For example, one algorithm that can very efficiently be used to do modular multiplication is like the Montgomery algorithm. And then, yeah, actually, let's say 15 years ago, this was a very important research topic to come up with efficient architectures for these modular multiplication operations, and also for elliptic curve cryptography based on modular multiplication. And then on the one hand, general modular multiplication that can be done like with any modulus. For those kind of operations, there were architectures proposed, but then it's also important to look at, for example, elliptic curve cryptography, where standard curves have, or standardized curves have been, or this should be curves, not cubes. Standardized curves have been proposed that have certain parameters, such that, for example, the modulus of the modular multiplication is fixed for these curves. And when you can fix the modulus of your modular multiplication, then you can also optimize your multiplication a lot. And of course, it makes sense to look at that. And then it's typically more useful to first do perform a multiplication and afterwards do the reduction separately, where in the reduction step, you of course can take into account that your modulus has a fixed value instead of here in this other architecture on the left, where we assume that the modulus can be like any input. And then of course it's possible to get very high performance when you make use of those standard curves with a fixed modulus. Yes, yeah, this is what I already said, I think so. Yeah, but it's important to remember, to repeat actually, because that leads us to the next slide. So like I said, the security of RSA is based on the computational hardness of integer factorization, the security of the Diffie-Hellman key exchange, and also of the digital signature algorithm are based on the computational hardness of the discrete logarithm problem. So when we do a modular exponentiation, it's difficult to find the exponent when you have the base number and the result of the exponentiation. And elliptic curve cryptography is actually similar, so it's based on the computational hardness of the elliptic curve discrete logarithm problem. What does this mean? Where we do a modular multiplication in the Diffie-Hellman and digital signature algorithm, we do a point multiplication in elliptic curve cryptography. So we start from a point on the curve, we multiply this point with a certain number, and the result will be again a point on the curve. And then when you know this base point and when you know the resulting point, it's very difficult to get this number that was used or this value that was used to do the point multiplication. So that's similar to a modular exponentiation. But the problem is that the problem here is that when quantum computers become available, Shor's algorithm can be used to calculate discrete logarithms and to do, and also elliptic curve discrete logarithms, and to do integer factorization in polynomial time. So that means that when sufficiently capable quantum computers will exist, that all these algorithms will no longer be secure and therefore cannot be used. And therefore, yeah, we got into the post-quantum crypto era, let's say. where researchers are in search for novel algorithms that do not rely on these underlying security features. So there is the PQC, or Post-Quantum Cryptography Standardization Competition, that was issued by the National Institute of Standards and Technology. And this was issued in, competition was issued in 2016. There are two types of algorithms that are that the competition is searching for. First of all, public key encryption algorithms, where when Alice wants to send a message to Bob, then she will use Bob's public key to encrypt her message and send the ciphertext to Bob. Bob will then use his private key, which forms a key pair with his public key, to do the decryption of the ciphertext, such that he can retrieve the messaging. And this is what we call public key encryption. Now, this is also used for key encapsulation in post-quantum cryptography, or can be used for key encapsulation in general. What does this mean? When Alice and Bob want to agree on a symmetric key to be used afterwards for symmetric key encryption, because symmetric key encryption is still much faster than public key encryption, which we see here on the slide. So it's good if Alice and Bob can agree on a key that can later be used then to do symmetric key encryption, because that's much more efficient than always doing public key encryption. And therefore, public key encryption can be used to encapsulate a symmetric key that can then afterwards be used by both of them. So the very simple way of seeing this is that Alice could just send to Bob, instead of this message, send a symmetric key to Bob that he then decrypts and afterwards uses for encrypting consecutive messages using symmetric key. So that's one type of algorithm that is part of the competition. And then the other type of algorithm are digital signatures. So what happens in a digital signature? Alice wants to send a message M to Bob. She uses her own private key that only she knows to encrypt her message, or actually to encrypt the hash of her message. So she just first takes the hash of her message and then encrypts the hash of this message with her own private key. And we call this the signing process, so signature process. And then she concatenates her message to this signature. Here we assume that confidentiality is not needed and that Alice just wants to send her message to Bob with a digital signature attached to that. There is no confidentiality because everybody that eavesdrops this channel can see the message in plain text. But of course, confidentiality can be added to this as well. On the side of Bob, Bob uses Alice's public key to then do the decryption or the verification process, such that Bob also obtains a new value which should be equal to the hash value of M. And of course, Bob also computes the hash of M after receiving M, because this is a one-way function. And then Bob can check if both are the same and then can verify if the digital signature was correct. So these are the two types of algorithms that are part of the post-quantum cryptography competition. And then on July 5th, after 3 evaluation rounds, NIST selected 4 candidate algorithms for standardization. First of all, in the category public key encryption or key encapsulation mechanism, there was Crystal Kyber, which is a lattice-based algorithm that was selected. Then in the category of digital signatures, Crystal's dilithium was selected, and also Falcon and Sphinx Plus. And there's 4 other algorithms that also will continue to the 4th round. And those are key encapsulation mechanisms. Those are BIKE, Classic McAleese, HQC, and SIKE. So these are lattice-based, Sphinx is hash-based, these 3 are code-based, and SIKE is isogeny-based. Unfortunately, or fortunately, 1 month after, more or less 1 month after this announcement, SIG was broken. Yeah, so this will not continue in the competition. That doesn't mean, by the way, that all isogeny-based algorithms are now broken. It was mainly in some of the additional computations in SIG that had nothing to do with the isogeny-based security properties. It was more in the additional computations that FPGAs is found. So it's not that isogeny-based crypto is dead. It's just that SIG. Implementation challenges. Again, when we look at public key encryption or key encapsulation mechanisms, we need a very large size, and I will show that on the next slide. Very large size of the public key, the private key, and or the ciphertext. In this case, which means huge computations. For digital signatures, also large size of public key, private key, and or the signature, because that's what we generate here. And complicated operations, leading to high computational and memory resources. Complicated operations, again, modular arithmetic, code-based cryptography, etc. So just to give you some numbers on these key ciphertext and signature sizes, when we look at public key encryption or key encapsulation mechanisms, and these are the algorithms that went on to the last round in the NIST competition. Of course, SIG, maybe we shouldn't look at anymore because it was broken. But as you can see, and these numbers are in bytes, these are huge public key sizes that are used also here, even for Kyber. Remember, when we looked at elliptic curve cryptography, for example, that the key sizes were 256 bits. And so these numbers are much, much larger. So these are bytes. Also, the private key sizes can be very large. For some algorithms, they are acceptable. But then again, the ciphertext. So here you can see that for HQC, the private key size is actually acceptable, but the ciphertext is super large. And then for other algorithms, the ciphertext size is acceptable, but then the key size is very large. And what do we mean with these things? Public key, private key, ciphertext, those are the things. So the keys that need to be used for the computations on the side of the sender and the receiver. So of course, it's important if these are large, then you need large computations, you need a lot more processing. And also the ciphertext here, that is what is being sent over the communication channel. So if that is large, then yeah, you need a lot more bits that need to be transferred over the channel. And of course, that also costs energy and delay, etc. So these are important things to look at. And as you can see in the post-quantum candidate algorithms, these things are much larger than in traditional public key crypto. Sorry. Yeah, and then here this slide is on digital signatures. So the second category, where we also look at the private key that is used to create the signature, the public key that is used to verify the signature, and then of course the digital signature size itself, because that needs to be transmitted over the communication channel. And then if you look at those algorithms that are still in the competition, then again, sizes are again in bytes, and so much larger here than here. The key sizes are much larger for Dilithium and Falcon than what we are used to in traditional public key crypto. And then these key sizes are actually acceptable for Sphinx, but then the signature size here is much larger. So it's kind of a trade-off. But as you can see, key ciphertext and signature sizes are much larger than what we are used to in traditional public key crypto. And then here again, some example architectures. So these are also, so this one is on Crystal Kyber, so that's lattice-based crypto, and the underlying operations that need to be executed are then modular or finite field arithmetic operations. Classic McLeese is a code-based algorithm. So here it's error correcting codes that are used. Yeah, SIG is now bit outdated, of course, because it has been broken. And then here we have like an architecture for a bike where you can see that a lot of memory is needed. So the current conclusions of NIST on these PQC or post-quantum candidate algorithm, post-quantum crypto candidate algorithms for digital signatures. Crystals, dilithium has strong security and excellent performance, and same goes for crystals Kyber. So this was proposed by the same team, and crystals Kyber is then key encapsulation mechanism. Falcon has a shorter signature size, which is also beneficial, and Sphinx Plus is an alternative that does not rely on the security of lattices, because NIST did not want to have only digital signatures still in the running that only rely on lattices, because if then a weakness would be found in lattice-based crypto, then there would be a problem. So that's why Sphinx Plus was also taken into account still. And then for public key encryption or key encapsulation mechanisms, again, Crystal Kyber, strong security, excellent performance. Bike and HQC, alternatives that do not rely on the security of lattices, just to be sure that an alternative is there. Yes, Psych, I should have crossed here as well, because Psych has been broken. It has a small key and ciphertext size. That was the main advantage. Like I said, it's not that all isogeny-based crypto has been broken, but Psych has been broken. So this should be removed, or I should cross it from this list. And then Classic Macaleese is a code-based crypto algorithm. The advantage there is that it's actually a much older algorithm, which means that it was already exposed to a lot of public evaluation. For all these algorithms, it holds that they are secure as long as nobody finds an attack against them. And the good thing about Classic Macaleese is that it has been around for much longer than the other algorithms here, even before the competition. And therefore, it is widely regarded as secure because many people had the chance already, or for a longer time already, to evaluate the algorithm and to try to find weaknesses. But of course, it also has the downside of having a large public key size. Okay, so yeah, I think it's clear that for these algorithms, because of the large key signature and ciphertext sizes, that parallel computation capabilities of FPGAs are very important, and FPGAs are widely used implementation platforms for these algorithms. But then there's also another cryptographic competition going on, also organized by the National Institute of Standards and Technology, and that's the lightweight crypto competition. That started, yeah, actually the process of preparing it started in 2016. But then a lot of input was asked from people all around the world to actually publish a call that everybody could support. And then the call for new algorithms was actually only published in 2018. Now, what is the goal of this competition? Of course, there is still the AES standard for symmetric key encryption. And AES is still considered to be secure as long as the key length is long enough. This competition searches for other symmetric key encryption algorithms that are actually more lightweight than AES, which means when you implement them in software, they take less ROM. When you implement them in hardware, the size of the chip or the occupied resources on the FPGA will be smaller than AES. And actually, where AES was a block cipher, what was just a block cipher in this lightweight crypto competition, it's not block ciphers that we look for, but authenticated encryption with associated data algorithms, or AEAD algorithms. This means that it's not only encryption, but also authentication of the data that is being done. And optionally also hashing should be. So this is the way it actually looks. So in this case, so what was there in for AES, there was also a competition and AES came out as the winner. The guidelines for that competition were just like, you have a plain text and we want to do encryption to get the ciphertext. In this competition, the list is searching for AEAD algorithms, which means that plain text should go through an authenticated encryption algorithm also to form a ciphertext just based on the plain text. That's one thing. But the other thing is that we want to form a tag that can be used by the receiver to check actually the integrity and also the authenticity of the sender of the data. And it's not only plain text information that is added to this tag, but also additional data, like for example, the header of a message that should not be encrypted. So nothing of this additional data should have an influence on the ciphertext, but only on the tag. So plain text information will end up in the ciphertext actually through the algorithm, and plain text plus additional data information will end up in the tag through this algorithm. And then additional data is just sent as plain text to the receiver. For example, the header of a certain packet. This could be the payload that needs to be encrypted. So you just send the header to the receiver and the encrypted payload, and then you have a tag that is there for authentication. We need a key for this. These are still symmetric key algorithms, so sender and receiver have the same key. And also a nonce is used for freshness. A nonce is a number that is only used once. So a nonce, for example, prevents a replay attack where an attacker just sends the same message repeatedly to a certain receiver. When a nonce is used in the computation, then an attacker cannot perform this kind of replay attack because the information of the nonce will be taken into account in the calculation of all these things. And the nonce is something that that can be sent in plain text or agreed upon between sender and receiver. But there are still 10 finalists in the running of this competition, and they are listed here. And the conclusion is expected late 2022. Now, why am I mentioning this? Because this lecture is also about FPGAs. There's also a call for benchmarking implementations targeting low-cost modern FPGAs. And this call was launched in 2022, so people are working on that now. The call is for benchmarking implementations on FPGA, but also for physical attack security or side channel security. So as opposed to the other algorithms that I showed before, which have large key sizes, large ciphertext sizes, large signature sizes, etc., and which need like huge parallel computation capabilities. In this case, FPGAs are used for benchmarking, targeting low-cost modern. The difference is, I must say, in these post-quantum crypto algorithms and traditional public key algorithms, there it really makes sense to use the FPGA also as an end product, because the advantage of using FPGAs is clear, like you need these parallel computing capabilities. In this case, the target is really like lightweight crypto. And of course, it's also for embedded software platforms, but when we go to hardware with these algorithms, then I would say that the main target would be like very low cost and low energy ASIC implementations. So here it's useful to use FPGAs to benchmark these algorithms and to see which one has the potential of being lightweight on an ASIC. But I would not say that FPGAs are necessarily like the target platform for end products using these algorithms, or not the main target. There can, of course, be applications where it's useful to also have these algorithms together with some other things on an FPGA. But I'm mentioning it because it might be interesting for you to have a look at this benchmarking effort that is being done at the moment. Okay, and then a few algorithms in cryptography that I didn't mention yet, but that are also useful to mention actually, because FPGAs are very good target platforms for these algorithms. Those are algorithms actually for secure computation. First of all, there's homomorphic encryption. With homomorphic encryption, as you can see here on the figure, what is the goal? For example, assume that you want to run a certain computation on some secret or private data in the cloud, because you do not have the computing capabilities yourself. You want to offload this computation. Then, of course, what would be the straightforward thing to do is to just execute whatever you need to do in the cloud. But then the problem is that the data on which you're executing your computations would be revealed actually to the cloud service provider. And that's typically something you don't want, of course, depending on the application. So what does homomorphic encryption allow you to do? Is to send encrypted data to the cloud and do the computations on these encrypted data, and then get in an encrypted form your processed results back. Of course, yeah, there's many categories in homomorphic encryption. You cannot always do everything you want, kind of computations. But the thing is that these are also, again, computations that can be highly parallelized and that rely on finite field arithmetic, typically. Also a bit similar to the post-quantum algorithms and public key algorithms, but then at a larger scale even. So here, speeding up these things with FPGAs is, again, a very good idea. Then another way of computing on secure data, actually, or doing secure computation, is multi-party computation. In this case, different parties collaborate to do a certain computation without revealing their own private data. So multi-party computation makes it possible to keep your private data to yourself, but still be able to compute something on the whole of all the data together. And this can also be useful. For example, let's say when there are multiple hospitals want to do some analysis on their patient data, but do not want to share patient data with each other, then it's possible to, for example, do some computations in the cloud without having to reveal individual data. So multi-party computation makes it possible to still do these analysis or computations without having to reveal individual data. And then there's functional encryption. In functional encryption, different users with different keys can compute different functions on specific encrypted data. This allows, for example, users with different rights to process different things on the same data and to get different results from the same data. You can again see this like in data analytics, for example. It could be that some users are allowed to do some computations on the data and other users are allowed to do other computations on the data without revealing the data itself. And again, for all these algorithms, these are computations on very large numbers, including mainly finite field arithmetic, and are therefore very suitable to be efficiently implemented on FPGA. And also here, FPGAs are very good target and implementation platforms for end products here also. Not like the lightweight competition where FPGAs are only used for benchmarking or mostly used for benchmarking. Here, FPGAs are really good end product target platforms. Okay, and then there's one more thing that I should mention that is also related to cryptographic algorithms, and that's physical security. So on the one hand, we want to protect our cryptographic algorithms from side channel analysis attacks. And side channel analysis attacks extract secret information from a certain device that is doing a cryptographic computation. And these attacks extract the secret information through side channels. So what do I mean with this? Imagine we have like an FPGA or CPU, any device doing cryptographic operations, for example, a decryption. Then this device does that using the secret key that is stored somewhere in the device. So we have some input data, for example, a ciphertext that should be decrypted into a plain text. So a sender sends a ciphertext to a receiver, and this is then the receiver system that decrypts the ciphertext into the plain. This is what we call the main channel. Now, whenever we do a computation on a certain physical implementation platform or system, then there are always unintended side channels. What are these side channels? For example, somebody could have a look at the timing information, like how long does it take to do a certain computation? An attacker or an adversary could measure the instantaneous power consumption of the device while it is doing the decryption operation. An attacker could also measure the electromagnetic radiation or emanation of the device while it is doing the crypto operation. Or a light can also be used as a side channel. So when or if the cryptographic operation on this device has not been implemented properly or has been implemented in a naive way, then these side channels reveal information on the secret key that is used in this device. So combining known data, with known data, I mean data that are being sent over a public communication channel, like the ciphertext here, combining this with side channel information, and then performing side channel analysis on these things can reveal the secret key that is used inside this cryptographic device. Another physical security threat are fault analysis attacks. So fault analysis attacks introduce computational errors to expose secret information. First, this first part, introduce computational errors. So how do we introduce a computational error in a certain system that is performing a cryptographic operation? We can do that by, for example, glitching the clock, which means like making one clock cycle much smaller. And as a result, for example, one operation or one instruction will be skipped. And if this instruction is, for example, the check in an access control system, whether the user is allowed or not, and we can skip this check, yeah, then this user might get unauthorized access. But in crypto algorithms, skipping an operation can also lead to data leakage. Another way of doing this is glitching the voltage, the power supply. So underpowering the device for a short amount of time. That if when we do this, then certain operations will also not be enough powered or will not have enough time to be completed, and we can also skip operations. Another more invasive way is to use laser fault injection to cause transient faults in a certain chip. Yeah, so that is to introduce computational errors. Yeah, to expose secret information. If we can tweak the crypto algorithm in such a way that it just skips a crucial operation, for example, then we can get secret information out of the device. So now going back to these side channel attacks, an example of how to see this is a simple power analysis on RSA. So when we look at the RSA decryption algorithm, then the main operation there is a modular exponentiation. So the ciphertext is used and raised to the power d, which is the private key. Modulo n. N is a public number. Everybody knows the modulus n. The ciphertext is what is being received by the receiver, and the receiver uses his own private key to do modular exponentiation, and what comes out is the message. This is the main thing in RSA decryption. Now, how can this be implemented in practice? This modular exponentiation can be implemented, for example, as consecutive modular modular squarings and multiplications. I should have written mod here, mod n, but you can just think that it's always there. So the typical algorithm that is used for this is left to right binary exponentiation. Because this d is a binary number, the private key, what we can do to compute C to the power D is to do, for every bit of D, we do a squaring. And only if the bit of D is 1, we also do a modular multiplication. And you can test this out with an example, and you can see that it works to use consecutive squarings and multiplications. But what we see here is that it says if di is 1, then we do a modular multiplication. If di is 0, we only do this modular squaring, which we always do. So that means that when we look at the power consumption, for example, this part of the power consumption, we can see that sometimes there's like this lower power consumption followed by again a bit lower and then higher, lower, higher, lower. This must mean that the lower ones are the squarings and the higher ones are the multiplications, because squarings can follow each other without multiplication in between. And when there's a multiplication, there's never like two multiplications next to each other. So what we see here is a squaring not followed by a multiplication, that must be a 0. Then a squaring followed by a multiplication, that must be a 1. Again, square multiply, that must be a 1. Then again, square not followed by mult, that must be a 0. So that means that what we actually have here between those lines is key bits 0, 1, 1, 0, or 6. And so that means that if the modular exponentiation is implemented like this, that just by taking one power trace of the device while it is running this modular exponentiation, we can extract the key bits based on a single power trace. And this is what we call simple power analysis. In some algorithms, like the AES algorithm, which is shown here, there are no conditional branches like in RSA, which means that the operations are always time constant and you always execute like the same sequence of operations. So AES looks like this. Plain text comes in. It's combined with the key through an XOR function. Then you have like 9, the same. This is AES 128-bit key. Then you have like 9, the same rounds consisting of 4 round operations, where at the end derived keys or subkeys are again added in the round. And then you have a 10th round, which is actually the same as these 9 other rounds, but then without the mixed columns. So, and then the ciphertext comes out. This is just something that always happens. So you do not have like if key bit is 1, then do this, which means that you cannot just perform simple power analysis the way you do it on RSA. So how can we still do power analysis on PS, for example? Why would we do power analysis? So like we said, one value is known. I know that in the example that I showed before, it was the ciphertext that is known, and then the key that we wanted to retrieve. In this case, we assume that an attacker knows the plain text, which might be in a real world scenario less relevant. Yeah, we can do the same thing starting from the ciphertext and with decryption. So it doesn't matter that I'm giving the example now for known plain text, because it can also be done in the same way for known ciphertext, but then for decryption. So we assume that the plain text is known or chosen by the attacker. The key is what the attacker wants to find out, is stored somewhere in the device. The device is doing the computation, and we want to retrieve through side channel information, through power information, this key. There is an intermediate value that will be measured through power consumption. That is a function of the plain text and the key. And we focus, for example, on this intermediate value. So how does an attacker do the attack then? First of all, he or she measures the power consumption that is related to the computation and or the storage of this value. So that means whenever this value is calculated, this intermediate value, or stored somewhere, the attacker makes sure to measure the current that is drawn from the power supply, which is gives us an idea of the power consumption, of course. Measures the power consumption at this moment in time. And the attacker does that for n different plain texts. And of course, always the same secret key, because we assume that the same secret key is used for a while before it gets updated, for example. But it's used for a longer time by the same system or the same device. So the key is always the same, and the attacker just triggers multiple encryptions with different plain text every n times, and measures the power consumption n times. Then an attacker can calculate the hypothetical intermediate values that belong to the plain text that is known every time, and based on a guess of the key. And actually, this guess only focuses on one byte of the key, for example. So when we focus, for example, on the least significant byte of the key, then what an attacker can do for these 8 bits or byte, the least significant bytes, there are 256 different possible values. The attacker also applies n different plain texts. So for each applied plain text and for each key guess, the attacker can compute what would be the intermediate value that we have here, because the attacker always knows the plain text and makes now a guess on this least significant key byte. And actually, this least significant key byte only has an influence on the least significant byte of this intermediate value, because these two functions do not shuffle the bits around. They just replace bits and do XOR operations. So an attacker can compute the hypothetical intermediate value here, and also the hypothetical power consumption that belongs to that intermediate value. An attacker does that by using a power consumption model. For example, saying, if I have here a byte that has 4 ones and 4 zeros, then I assume that my power consumption is this high. If I have a byte here that has only 1 1 and 7 zeros, then I assume that my power consumption is this high. Or if I have a byte here that has a certain value, and I know now that all 8 bits flip values, then I know that my power consumption is much higher than when none of the bits flips. So there's different models to be used for calculating hypothetical power consumption. And this is what the attacker does. Then, of course, the attacker also really measured what happens here. So an attacker actually predicts what is happening here and also measures. And then he or she can perform statistical analysis and actually correlate the measurements with the hypothetical values to see what was the correct secret key that was used here. So as you can see, we need multiple measurements, and we need to do some statistical analysis, but we can still get the key out. In the RSA example, we only needed 1 power trace and no analysis was, we had to look at the trace to see what the bits were. So requirements for successful attack are that all power traces should be aligned that are measured, and that the attacker can calculate the hypothetical intermediate values, and also this hypothetical power consumption based on a specific power model. Countermeasures can be categorized into masking and hiding techniques. So with masking, what we do is we break the correlation between the data that are processed and the algorithm that is executed. So that means that we will not process the actual plain text, but we will process a masked version of the plain text. And this mask is a random number that is for every execution of the algorithm different. So remember, the attacker had to take like multiple measurements, multiple guesses. If now for every one of these measurements, the plain text is masked with a different random value, then these values cannot be correlated anymore. Hiding means that we break the correlation between the processed data and the side channel information. That means that we really process the plain text as it is, but we make sure that what we measure does not correlate anymore with this processed data. To give some examples, masking example on AES, very simple. The additive mask, for example, we do not process the plain text, but we process plain text XOR random value. And we can also add another mask to the key. So this is called Boolean masking. This random mask is unknown to the attacker. And if we, for every new measurement that we do, make sure that there's a different mask here, an attacker cannot correlate the measurements anymore. But of course, and then at the end, of course, we need to remove the mask to get the real ciphertext out. Now, if these were all linear operations, we could just add the mask here and remove the mask here. But unfortunately, there are also, not unfortunately, we need that to have strong crypto, but there are also nonlinear operations. And then this sub-bytes operation here that is used here 9 times and also once here, and also in the key expansion. Those are nonlinear operations where we need to do something special to make sure that the values that we are processing here are still the correct ones. If you do this, it's still possible to perform a higher order attack, which means you take multiple measurement points and then still try to retrieve the secret. Hiding countermeasures, like I said, we process the data, the real plain text as it is, and we do not mask the plain text, but we try to break the correlation between the data that we process and the side channel information. For example, by making the power consumption always constant, we can have a balanced program flow. For example, this simple power analysis example for RSA, where we could see which were the 0 and the 1 bits. If we insert dummy operations to make sure that we always do a squaring and always do a multiplication, then you cannot see the difference from a single power. We can also use special logic design styles, for example, dual rail design styles, which means that whenever we process a 0, we also process a 1. Pre-charge logic, which means that all, let's say, intermediate values are always pre-charged to a certain value and are only discharged when needed. This way you can make sure that there is no distinction between the change of a bit and a bit staying constant. We can also make the power consumption random, like having insertion of noise engines, random insertion of dummy operations, of shuffling operations, random changes of the clock frequency. Now, where do FPGAs come in here? We can use dynamic configuration capabilities of FPGAs for randomizing. For example, the first proposal here was to use power and fault analysis resistance in hardware through dynamic reconfiguration. And there was also a paper on like side channel protection with like dynamic logic reconfiguration, which focused more on the lookup tables itself, like only changing, dynamically changing the lookup tables without changing the routing dynamically, which is much more efficient. And if you can do that and still have like strong protection, then that's a good way to go. And then this is an overview paper. So. Okay, so we talked about cryptographic algorithms, which type of cryptographic algorithms are challenging to implement and where we can use FPGAs for that. We also said something about post-quantum crypto algorithms, where it's even more challenging to do the implementation and where FPGAs are even more useful. And then also something about side channel analysis and how the dynamic configuration capabilities of FPGAs can be used as countermeasures. Then there's a last part to this presentation, and that's on network intrusion detection, so other topic. Okay, so why is network intrusion detection important? Well, if we look at the internet, then there's an increasing amount of network traffic. The network bandwidth goes up and up. And when you look at the news, there's every day another attack, so that the attack surface is also increasing. There's many types of solutions. But one solution we can think of is to use intrusion detection systems. I'm not talking about the typical firewall that blocks certain packets to come through to a network, but more like an intrusion detection system that can be inside a network, for example, checking if everything that happens is still properly happening and if there's nothing strange going on in the network traffic. So what does a network intrusion detection system do? It monitors the network traffic and detects whether there's malicious traffic. So it just looks at the packets that pass by and checks if there's something strange. Now, why is this important now to use FPGAs here? Well, because there's so many data that need to be processed, and because the speeds at which these data go through the network are becoming so high, it's not anymore possible with a traditional CPU to keep up with this speed and to make sure that we have enough memory that can also be accessed at high speed to do all this monitoring. When we look at most recent FPGAs board, then they can deal with network speeds up to 200 gigabit per second, and there's even boards out there now that can handle 400 gigabit per second. So that's actually perfect to deal with this high throughput traffic. And also these FPGAs are very large, so they can in parallel do network measurement very fast. If we want to do on-the-fly intrusion detection, then processing of data also needs to be done at line speed and at the speed that the data are being communicated. And therefore, we really need FPGA boards. Now, if you look at intrusion detection systems, then there's different types. There's network-based intrusion detection systems that look at the network traffic that goes by. There's also host-based intrusion detection systems that are installed at a certain host or a certain entity in the network and check if anything goes wrong there. Now we focus on network-based intrusion detection systems, and there's actually three main types of mechanisms that are used here. One is pattern matching, then flow measurement, and machine learning. So if you look at the first technique, pattern matching is used for the detection of fixed rule violations. And these rules are typically based on regular expressions, for example, like the snort rules. So these rules look at the packet and just check certain fields and see if some rules are violated. This can be implemented through deterministic finite automata or non-deterministic automata. This is actually like something, let's say, that has been going on for a longer time and has been used for a longer time. But yeah, FPGAs can be useful here to in parallel process all these things. Then when we look at the second technique, flow measurement, this is, and also all types of attacks can be detected here as long as they can be put into rules. Second technique is flow measurement. Flow measurement is not used for any type of attack, but it's used for the detection of large flows. For example, in distributed denial of service attacks, where a certain sender or multiple senders flood the whole network with messages or packets or traffic, such that some services are no longer available. So flow measurement is used for detection of large flows. What is a flow? A flow consists of all packets that have the same flow ID. And flow ID is typically consists of the source IP address and destination IP address, source port and destination port, and sometimes also the protocol that is used, like for example, HTTP. Flow measurement contains a lookup part and a measurement part. So what typically happens is a network flow comes in, a parser checks to which, actually a network packet comes in, parser checks to which flow this packet belongs, and checks in the blacklist whether this flow ID, this packet with this flow ID should be dropped or not. And because we assume that we keep a blacklist of malicious flows. Once we have this, so all the values that are in this blacklist, all those packets should be dropped. If the flow ID is not or not yet in the blacklist, then the flow passes on to the measurement unit, where we keep track of how many packets this flow has been sending, for example, in the past that many milliseconds or something. So we have a measurement unit that checks whether this flow is sending above the allowed threshold in terms of number of bytes, number of packets, etc. If this flow exceeds the threshold, then we write this flow ID to the blacklist. If it doesn't, then we pass the packet on, and it looks like nothing has happened. So this has to be done at line speed, at the speed that the packets come in, because we don't want this to slow down the whole communication. So actually, for a packet where nothing is wrong, this should just look like a wire, actually. Now, what is the challenge here? Why is this so difficult? Because, yeah, you would say, this is just a lookup. And this here is just keeping track of how much each flow is sending. Well, this becomes challenging when there's a large amount of data and when these data come in at very high speed. Then it is no longer possible to have lookup architectures and measurement architectures that can deal with this, these amounts of data at this high throughput. And then the only option we have is to go for probabilistic data structures. And those are data structures that can say with an accuracy of, for example, 99.9%, this packet is in, this flow ID is in the blacklist, or with an accuracy of, for example, 99.9%, this flow is not sending above its intended threshold. So we can save memory by using probabilistic structures instead of exact data structures, and we can do faster lookups and faster measurements by going to probabilistic data structures. So what are these probabilistic data structures then? Like when we first look at the blacklist, then an exact data structure would be a content addressable memory. It has no false positives, no false negatives. When you ask, is this flow ID in the list? It will, with 100% accuracy, tell you if it's in the list or not. But it has a relatively high area, high power consumption, and when the content addressable memory becomes very large, then the operating speed becomes too slow. And that's why we go to probabilistic data structures, like, for example, Bloom filters, which have much higher operating speed, lower area, lower power consumption, but have the disadvantage of having false positives. And there's also cuckoo filters. I'll show you now an example of what such a Bloom filter or a basic Bloom filter looks like. So, for example, we want to do a lookup. So in a Bloom filter, in a basic standard Bloom filter, we have a memory array with 1-bit cells. This is an example of Bloom filter with 6 1-bit cells. These cells are indexed by K hash functions. So when we want to add a certain flow ID, so this 96 or 104-bit value, if this were a normal memory, we would just add the whole value to this memory. So in this case, we perform multiple hash functions, multiple different hash functions, in this example, 2 hash functions, on this value. So hash function 1 results in a certain value, and that value is used as the address in this memory array, and at that address we will store a 1. We use hash function 2 that also results in a certain hash value. That hash value is used as an address in which we will store a 1 in the memory. We add a second value, x2, second flow ID, for example, that we add to the blacklist. With the 2 hash functions, h1 and h2, which result in 2 1s that are being written again. We add x3. X3 points to one memory location that was also already addressed by x2, and it points to another memory location where we create an additional 1. Then we want to query. Now we are doing the online thing, and a flow or a packet comes in. We want to check if this flow ID is in the blacklist or not. So we need to check if x1 is part of this memory or not. So we take x1, we perform h1 hash function and h2. We check if there are 1s in the memory. Yes, there are 1s. So we say x1 is present in the memory. We do the same for x4. H1 leads to this location, H2 leads to this location. There's a 0 in this location, so we can say X4 is not part of the memory array. But, for example, we want to check if X5 is present. We didn't add X5. The hash functions H1 and H2 point to this first memory location and the fifth memory location, and there are ones there. But 1 came from X1 and 1 came from X3. So we have 2 ones. We need to conclude that X5 is present in the memory structure and say like X5 is there, but this is a false positive. And of course, you can see that when you make this memory size larger, you get less false positives. Also, you can play with the number of hash functions that you use, etc. But we can really get accuracies of above 99% with this type of structure, while reducing the memory a lot, because otherwise we would really have to store everything in an exact. So that's for the blacklist. So, and of course, there's actually relating this to FPGA design, there's many algorithmic and architecture improvements on this standard Bloom filter structure that are very suitable to be implemented. Then another part in the flow measurement technique was the measurement unit. If we use associative counter arrays, then they are accurate, but have a high memory overhead because of exact counting and low operating speed. So what we need to do here, and as a reminder, flow IDs come in, and we need to keep track of how much every ID has been sending. So flow ID number 1, we keep like a counter, and every time a new packet comes in, we update or increase this counter. We do the same for flow ID 2, flow ID 3, but of course there can be many flow IDs. The volume becomes very high, the speed is very high, etc. So it is not possible to follow at such high speeds at line rate with associative counter arrays, which are exact data structures. And therefore, we also go to probabilistic counting architectures, like sketches or counting Bloom filters. They have a higher operating speed, lower memory overhead compared to associative counter arrays, lower energy consumption, but they have a certain probability of error. Now, how do these work? This is a very simple example of a count-min sketch data structure, or CM sketch. For example, flow packet comes in with flow ID X1. Then we use 2 hash functions again to update this memory structure, which is now a 2D memory array of counters, indexed by k hash functions, and k is 2 in this example. So H1 points to this memory location, which means we have a counter here at each memory location, and we do this counter +1. H2 points to this memory location. We also have a counter here, and we also increment this counter. Then X2 comes in. The hash functions point to 2 different memory locations where we do the increment again. Then X1 comes in again, and because this is the flow ID, and we get packets of multiple different flows, but the goal is, of course, to measure whether a certain flow is sending too much or not. So, of course, there can be packets then that belong to the same flow as what we had before. So, of course, X1 points again to these 2 same locations. So we do +1 for both locations. We go from +1 to +2. Then X3 comes in. X3 points to this location and to this location. So the first location, hash1, is shared with X2 here, and the second location is a new one. So we do +1 for both, which means that this becomes +2 and this becomes +1. Then we want to query. We want to see which flow is sending too much. We want to check X1. We, of course, use the 2 hash functions, and we check what the values are at those 2 locations. Those values are 2. So we say the count value for X1 is the minimum of those 2, and that's 2. Then for X2, we look at those 2 locations that we have here. We see a 1 in one location and a 2, which was a contribution from X2 and from X3 here. But we take the minimum, and the minimum is 1. So we conclude that the count value of this flow is 1. Then we have x5, flow that was not even there. And the two hash functions point at this location here and this location. The minimum of those two is 2. So we have to conclude that x5, that there were 2 packets with flow ID x5 that came into the data structure. Well, this is actually not true because x5 was not there. This way you can see that what you get here is not always correct. But of course, if you increase the data structure, play with the number of hash functions, etc., you can do a lot. And still, this data structure is much smaller than an exact data structure and much faster. Yeah, what is also important here is the hash function itself. So both for, I'll go back to the lookup architecture, we needed hash functions here. Also for the counting architecture, we needed hash functions here. And of course, these need to be fast enough because they determine also the speed of the lookup and the query. And that's why when we look at, so actually these are non-cryptographic hash functions. So cryptographic hash functions have to adhere to many more security properties than non-cryptographic hash functions. Non-cryptographic hash functions, the most important thing there is that we avoid collisions of the hash functions. With cryptographic hash functions, there are many more properties that need to be fulfilled, like pre-image resistance, second pre-image resistance, and so on. In this case, the existing non-cryptographic hash functions that are there are actually all oriented towards fast software implementations. But since we see now that we need to use FPGAs for these high speed, high bandwidth, high amount of data applications, it's important to also have a look at which of these hash functions or which hash functions perform optimally in hardware or on an FPGA. And that's an experiment that we did by looking at new non-cryptographic hash functions. And actually the way we started is to take cryptographic permutations and reduce them in such a way that they might not be cryptographically secure anymore, but they provide enough or sufficient avalanche properties. And avalanche properties tell us how well, for example, when you change one bit at the input, how this has an effect on all the bits at the output, what the probability is of when changing one bit, what the probability is of that the bits at the output change, etc. So all these properties are checked. And then we found out that actually we can have a lot increased throughput compared to existing hash functions that were actually developed for software. So all these that are proposed here are just one cycle hash functions that work at a very, very low latency. Many optimizations have also been proposed at the architecture level, and there's also a recent example a few years ago at the FPL conference for cardinality counting, so also for counting the cardinality of flows. And then there's a third technique to do network intrusion detection, and that's machine learning. So machine learning, the advantage is there, we can use machine learning to detect. So actually to summarize a bit, pattern matching was to detect rule violations to fixed rules. This flow measurement is used mainly for DDoS attacks to check if a certain flow is sending above the intended limits. And the third technique, machine learning, can be used for the detection of known attacks, just like pattern matching, but also for detecting deviations from normal traffic, like anomaly detection. There's a large variety of data sets, feature selection methods, and algorithms actually out there. These are the commonly used data sets. Some are outdated or consist of simulated traffic, but these are the ones that are used in research papers to compare results. And there's also different types of algorithms used in this space. When we look at results of the last years, let's say, then the challenges are that the throughput is either low, or when so for some of these results we can get to a higher throughput, like for example here, but these networks are then so simple that their detection capabilities are quite low. Or we can get to a higher throughput, but then or we can have higher detection capabilities, but then again the throughput is lower. So this is kind of a trade-off. Sorry, this is wrong. This is from something else. I should have removed this. So we recently had a paper at FPL 2022 where we presented like some advancement in this space. It should not be on Wednesday. It should be something. I'm sorry. Then if we compare these three techniques, pattern matching, flow measurement, and machine learning, then we can see that when we look at the coverage of multiple attacks, that machine learning covers the most, because we can detect existing known attacks, but also deviations from normal traffic, which we call anomalies. When we use flow measurement, that's only used for like large flow detection or DDoS attack detection. And pattern matching, we can detect multiple types of attacks, but only based on those fixed rules which have to be determined before. Then in terms of accuracy, pattern matching is perfectly accurate because we just do an exact pattern matching. Or when we do exact pattern matching, it's perfectly accurate. When we use flow measurement, then we get accuracies of like above 99% if we choose our probabilistic data structures well. And with machine learning, yeah, it depends on, it's a trade-off between throughput and accuracy. But there the problem is probably highest. And also here, yeah, what is typically desired is that we have some sense of explainability also of the machine learning model. So that's also a big challenge. Then expert knowledge, yeah, ease of maintenance, pattern matching, that would be like the easiest because these are fixed rules actually. For flow measurement, yeah, might become a bit more difficult, but for machine learning, yeah, we need more expert knowledge actually to set up the right neural network and the right implementation, high throughput implementation to be implemented. Ease of design. Sorry, I'm actually I'm mixing two things up actually. Sorry, ease of maintenance, pattern matching for the user of the system. This is the most difficult, and because there needs to be policies, the rules need to be determined. So this is the most difficult. Flow measurement, yeah, yeah, we need to determine like which hash functions, what's the size of the data structure, etc. So these things need to be determined. And for machine learning, actually, it's much easier because we can just have our machine learning algorithm running there and detecting all attacks. We don't need to come up with policies about which rules to implement, which not, etc. But in terms of ease of design, and that's what I was actually talking about, it's much harder to have a high throughput machine learning algorithm on an FPGA than to have like just pattern matching techniques on an FPGA, for example. Detection speed is the highest in pattern matching and the lowest in machine learning if we want high accuracy. And the same goes for hardware efficiency. So conclusion of this lecture, I think timing is also fine. If we look at cryptography, then FPGAs are suitable implementation platforms, especially for post-quantum crypto algorithms and also these secure computation algorithms, because we can use the embedded memory blocks, Dsp blocks, parallel computation capabilities on large numbers, etc. Also, dynamic reconfiguration can be used to protect against physical attacks, side-channel attacks, fault attacks. When we look at the intrusion detection part, then pattern matching and flow measurement are well studied and offer high throughput, but there's a lot of room for improvement in the throughput of highly accurate machine learning architectures for intrusion detection. And with this, I conclude the lecture and I'm happy to take questions.
I have a question.
Hello? Yeah, please. Yeah. Hello. Yes, I hear you. Yeah.
So you said that the FPGAs are more suitable for the security algorithms that require a huge is more suitable for those which involve more sophisticated computation and power requirement? And is it the reason why it's not suitable for the embedded, implementation of the algorithms on embedded devices? Yeah, I mean,
I think for embedded implementations, FPGAs are probably overkill. Low cost is there also an issue. Like you want to have like low cost off the shelf microprocessors there, and when the requirements on speed, for example, are not that high, and requirements on cost are very high, like it should be super low cost, then an FPGA is just not a suitable implementation platform. And it doesn't make sense to go for an FPGA because you would pay more. And since you don't need the speed up of the FPGA, then that doesn't make sense actually. So it's mainly like that it would be overkill and not cheap enough, I would say, to go for FPGAs for low-end embedded applications.
Okay, and today we have the concept of federated learning, where we see that, and that's one of the requirements. I mean, it's because of the security concerns that this particular style of learning is gaining popularity. Do you find FPGA suitable in such kind of federated learning-based models implementation?
Yeah, FPGAs can definitely handle the computations, but again, there comes the question, like, how suitable are FPGAs for these? Like, if you have like a large, I don't know, system consisting of many low-end devices that should do part of these computations, then FPGAs will not be suitable. But if you're in like a more high performance distributed setting, then FPGAs could be suitable implementation platforms. So it's not that FPGAs would not be capable to do these computations, but the question is, are they suitable implementation platforms for the higher level application that is making use of learning? So
where do you find FPGA presently in this whole security concern? Which kind of applications do you really?
Yes. So if I look at projects that we have been doing and where questions came from governments or companies, then definitely in space. So space applications there, FPGAs are heavily used actually. And the reason is there also that like when something happens related to single event upsets or radiation, you can easily also reprogram your configuration memory and restore everything. So and there are also FPGAs that are like radiation hardened, and actually FPGA vendors are really also aiming at those markets. So in space, definitely. And then questions that we got from governments and companies are also to like for those applications that require like a bit lower volume systems. For example, one question we got was for interbanking terminals. So these are needed less than those terminals where the users go to, of course, but still speed was important. And then it was also important to the whole cryptographic suite, like many algorithms needed to be implemented on this interbanking terminal. There were some speed requirements. It was also clear that this would not be mobile or something, so power consumption was less of a concern. But what was still important was that the interbanking terminal could be updated later with new algorithms, or when new attacks were found, that an update could be done, while it was also clear that general purpose CPU would not fulfill the speed requirements in this case. So I would say in general, definitely for specific application domains like space, and then for the rest, like a bit lower volume probably than those for which you would make an ASIC and just have like 1 million samples or something. So a bit lower volume applications that still need higher speed than what you could achieve on a general purpose process.
Okay, so suppose I considered some security design, what should be my concern for choosing an FPGA? How do I convince somebody that FPGA we should go for an FPGA based solution? Is it the speed that should be a concern? That should be differentiating factor?
It's mainly performance. The reason is mainly performance why FPGAs were chosen. Yes.
And when you say speed, you mean the speed of computation or the speed at which you work with the data, right? I mean, that as you said that it's of the say gigahertz order of processing the data acquisition. Is that the concern or the computing speed of the computation? Yeah. What should be the concern?
I would say both. So it's computational speed for sure. You can get high throughput through parallelism, etc. But then also when you look at the level of the board now, and like all these like high throughput or high bandwidth Ethernet connections that are being provided, for example, on Xilinx FPGAs, but also on others, that gives you like a nice solution, a nice board to really have applications that can also deal with these high throughputs of data. Actually, so these are really foreseen on the boards on the FPGAs. So it's actually both.
Okay, so should it be an ideal combination of having an embedded processor and an FPGA-based kind of a configurable unit when you think about and security design? Or
what is typically done is that there is an embedded processor also on the FPGA. So like if you need like high data throughput, then of course the data should not go through your processor, but the processor is used to control things. So typically in a larger FPGA design, there's always an embedded processor.
Okay, so
and some boards are really supporting this very well. Yeah.
Which part of the computing, the algorithm is actually tried out on the configurable part, and which part is on the embedded part? Is it the
it's of course that part that is the bottleneck in terms of speed then typically. So but if you look at, for example, these network intrusion detection systems, then this whole pipeline, let's say, where the data goes through, so we want data to come in at line speed, at the speed that the data are traveling through the network, and then the measurement unit is there, lookup table is there, lookup unit is there, and then data that are allowed to go through at the same speed without any delay. And of course, next to that, you can have like a processor that is configuring small parts of this pipeline or checks like a few things, but that can be at lower speed. Then it's like the path that the data takes, that has very high performance requirements, but all the other monitoring or controlling things, logging things can be at much lower speed. So that can be the processor.
Okay. Thank you, and thank you very much for your lecture. It was really nice.
Thanks a lot. Thank you for the question. I apologize for my voice and the interruptions. More questions? Yeah, if not, I guess we can close. I don't know if somebody's here from the organizer.
Right. Yeah. So if there are no more questions, I would like to say that we'll upload the recording by maybe possibly tomorrow or today midnight. So you can go through the lecture again, and you can contact Nele in case you have any more questions. So yeah, great. Thank you. Thank you for the talk.
Okay, it was my pleasure. Thanks a lot for inviting me to give this lecture.
Yeah. Okay. Thank you, everyone. Bye.